Today's workshop of the National Network of Health Surveys, our work on advancing the disaggregation of ethnic and racial data through technical assistance, training, and case making. I am AJ Scheitler, and I'm the director of the network, and I am joined today by several of my colleagues, Dr. Ninez Ponce, Dr. Sue Babby, and Dr. Riti Shimkata, and also our communications director, Tiffany Lopes, who we all may be interacting with you throughout today's workshop. Please, everyone is muted, so you won't be able to ask questions of us. So if you want to ask questions, please use the Q&A function. That is where we are going to be directing questions to the panelists at the end. If you want to utilize the chat for general comments and discussion or questions amongst yourselves, that would be great. But if you have a question for our presenter today, please utilize the Q&A function. So as I mentioned, this is the National Network of Health Surveys, and we are dedicated to try to help both surveys and other data sources, which are often paired with surveys, to produce very high quality data for both researchers, policymakers, and just average users who want to get involved with improving health equity in this country, which is very much on the forefront of a lot of people's minds right now. So we're very happy to be engaged in this work with so many people who really want to have good data at the ready to really make informed policy. So we are working to improve the collection, the processing, and the reporting of disaggregated data. So this workshop series is really going to touch on all parts of the process of data. So whether or not you are a data custodian or a data user, this is a good place for you to come and please be a part of our discussions. And we are going to be doing these workshops. And at the end of the workshop, we ask all of you to fill out a short survey, both about how our workshops may have helped you, but also additional topics of interest that you have, additional barriers that you're experiencing in getting really good disaggregated data so that we can craft future sessions to really help everybody. These are our upcoming sessions into the new year. This is our final one for 2020, and we're ending it on a bang. But we have 3 that we are already planning for the beginning of 2021. If you are registered and here today, you are already registered for these three, but look for coming announcements about the dates when we get those finalized in January or February. For today, we are going to learn what we can rely on technology to do to help us address the barriers of data disaggregation. And we are very lucky today to have as our panelist, Dr. Scott Camarata, who is a professor at UCLA with multiple department affiliations. And he is going to help us understand the capacity of machine learning to help address these, and then give us a taste of some of the technical things we were going to want to consider if this is a solution to help your project to improve your disaggregation. So with that, I am going to hand it over to Dr. Camarata.
Okay, thanks so much, AJ. I'll do my screen share here.
Okay.
Let's see. Okay, can everybody see that? Is that good?
Yes, okay. We can. Thank you.
Perfect. Thanks, AJ. Well, thanks so much for having me. It's great to be here. This really is a fantastic workshop series. And as was mentioned, I'm going to be talking about machine learning methods. And I'm going to assume you don't know much about it. So I'll start pretty much at the beginning and talk about some ways that they can be used in addressing health equity research and data disaggregation. So I'm actually going to launch right into an example. I know if you're like me, it's kind of hard to hear concepts and things without anchoring it to something concrete. So I'm just going to launch into an example to begin with, start with something you're probably familiar with, Then I'll go into some definitions. I feel like we hear a lot of definitions with machine learning, AI, natural language processing, kind of put that together. Then I'll talk about some specific use cases for this workshop today, write-in responses on surveys, and inverse probability sampling weights. You want to look at strategies for that. And then I'll end by talking about software and some other considerations if you want to do this, and some caveats to leave us with. While these methods can offer a lot, we have to be pretty mindful when we apply them, make sure we apply them correctly. So let's launch right into an example. This was taken from a paper that I actually came out with recently with a group of people. This was a HRSA study. The original data was collected to evaluate the impact of an intervention on HIV care continuum outcomes among youth and young adults living with HIV across the US. The purpose of this particular paper was to do a secondary analysis to really better understand the characteristics of people living with HIV who search for health information on the internet. So we wanted to understand the characteristics. And then we also wanted to see if we could build a predictive model to actually be able to predict whether or not somebody would seek health information on the internet. So why did we want to do this? Well, working in this line of research, digital health interventions can offer a lot to reach populations that don't necessarily have access to clinic care, can provide health information. And so as we think about digital health informations, we want to know, can we better tailor them for the people that really need them? In things like looking up health information, those are important considerations. And we also want to know, the right people to deliver the interventions to, who's likely to use them. So there's a predictive element to this that extends beyond the typical regression analyses we might do just to see what variables are correlated to the outcomes. So the study design, our primary outcomes are really yes, no indicators assessed at 6 months after the baseline to know whether or not somebody looked up general health information on the internet. It's all self-reported. And we used a whole host of baseline predictors, everything from socio-demographic characteristics, healthcare utilization scales, time since HIV diagnosis, substance use, mental health measures. So this is actually a very classic scenario for machine learning where you have a lot of predictors. You don't necessarily come in with a conceptual framework like we do in health policy research sometimes, where we have a primary regressor, we might have a few adjustment covariates. Here, we really were exploring. Machine learning is well suited for these types of situations. The sample we had was 716 participants, ages 18 to 34, very reflective of people living with HIV in the United States. There were 10 demonstration sites across the US, all the way from Los Angeles, San Francisco, New York City, Texas, so around the US. Some of the key characteristics we wanted, mostly Latinx or African American, Black. Other key characteristics, representation from those who self-identify as gay or lesbian, sexual orientation. We wanted representation from transgender women, basically people who are hit hard by the HIV epidemic. We wanted them represented. And so that's another key point when we think about machine learning and applying it. It's really important to have that representation of the people that you want to reach in your data. Because if you don't have that, machine learning can't really do much for you, or it can make things worse in the conclusions that you draw. So the first question you could ask me is, well, okay, what you've described so far, can't we just use traditional statistical methods to address your goals? And let's revisit the goals again. So first, we wanted to determine characteristics that predict internet health information seeking. Who's going to get online and look up health information based on their characteristics? When we enter this machine learning environment, instead of referring to independent variables, we usually refer to them as features or inputs. So I'm going to switch that language as we get on in the slides here. So we're really, when we talk about selecting covariates or predictors, we talk about feature selection. That's the language we often use in ML. So that was the first goal, to better understand the characteristics, but also, can we take those characteristics and actually build a predictive model? So you could ask me, well, the first goal kind of sounds like variable selection. If you want to figure out which characteristics are predictive, can't we just run a stepwise regression on the full sample to achieve that first goal? Well, the answer is yes, we certainly could, but there is actually a problem. And that's something that's not always talked about in traditional statistical methods. That's the problem we refer to as overfitting. If we just take all of our sample, the 716 participants, and we use that same sample to select variables and then evaluate how well the variables actually predict in the same sample, we're not really getting a fair shake. We really would want to see how does this model perform in a new sample. Otherwise, we're just going to overfit if we're trying to evaluate using the same sample. So that's a key element of machine learning. We want to do a better job of predicting by looking at a new sample. We can certainly, as we do with traditional statistics, we can certainly calculate fit statistics. Calculating p-values is pretty tricky when you get into variable selection methods, and that's almost a whole lecture in of itself. I'm just going to say really briefly that the p-values are not correct. If you do variable selection and then try to calculate p-values, you're going to be off in determining significance levels. And, even if aside from the whole issue with p-values and variable selection, let's think about what the p-value really tells us for a minute in terms of prediction. Is that useful? And I'm going to use kind of a simple little simulation here. It's almost kind of silly, but I think it gets the point across. Let's say we have two variables, and we sampled them. In this case, I just sampled them from a bivariate normal distribution, X and Y. And I'm going to simulate two data sets, calculate the correlation coefficient between X and Y. And of course, we can calculate a p-value from that correlation. So let's say in the first data set, we get a p-value of pretty close to 0.05. You'd almost say that's borderline. Now, I know as a statistician, it's taboo to say that. We are moving away from kind of treating 0.05 as that magical cutoff. We shouldn't do that. But for the sake of this discussion, I'm going to use that language. 0.05, kind of borderline. What used to get you questionable is something would get published in a journal. But in the second data set, we actually get a p-value of 0.03. We might get more excited about that. That's looking pretty good, but what does that p-value really tell us in terms of prediction? Well, it turns out not a whole lot. So here are the two data sets side by side, and here is the, what we get, the correlation and the data points between X and Y. If you look at the plot on the left, I kind of withheld some information from you purposely when I gave you those p-values initially, because I wanted to really make the point is sometimes we jump up and down about p-values, but we stop to think, okay, the data set on the left, that only had 5 data points. The data set on the right had 100. So the p-value is very sample size specific. The one on the right had a much lower, not much, but it had a lower p-value, but we see the correlation coefficient is actually only 0.22. And the correlation coefficient on the left is much higher, 0.88, and we see that in the actual underlying distributions I used for simulation, the correlations are similar. So the point being here, if we just looked at the p-value, how confident would I really be in using X to predict Y? Well, just looking at the scatter of points on the right-hand side, even though the p-value is 0.03, I probably wouldn't be all that confident about using X to predict Y. So we really need to think about a different framework in the machine learning world when we really want to know how well something predicts something else. And especially if we think about surveys and we're using values to say help fill in written in responses, we want something that's pretty accurate. P-values are just not going to cut it. So what did we actually do in this particular example? What gives it the machine learning flair? Well, one characteristic of machine learning is that you're going to split your data. There's different ways to split it. There's not necessarily one right way. But what we did is something that's often done is you take the data and you randomly split it, say, into 75% into one group and 25% into the other group. That 75% is what we're going to call our training data. That's the data set we're actually going to use to build the regression model. And I'll talk about the model in the next slide. But regardless of what model you end up fitting, that training data is where you're going to do it. You withhold what we call test data, here about 25%, to actually evaluate the model. Now we're actually going to see how it did. And we call this our out of sample prediction. We can use, if the outcome is continuous, we can use R squared, other fit statistics, but the key is we're not calculating those in the same data we use to fit the model, using a different data set. In this particular example, the outcomes were binary, so we used area under the receiver operating curve, as is often done for binary measures, and there's certainly a whole host of other fit statistics for binary measures. In this case, I have an AUC plot on the right there. The prediction is not too bad. We got to 0.76 for area under the curve. If it had been 0.5, that's basically telling us our prediction is doing no better than a coin flip. And so we're pretty happy with the 0.76. So let's talk for a minute. We've split the data into training and test data. Let's go back and ask the question, okay, so what modeling approach should we use? Well, we actually chose to use something called lasso regression, and some of you might be familiar with this already. The term is written out there, least absolute shrinkage and selection operator. So why did we use this lasso method? Again, if we're selecting variables, why not just use maybe our familiar stepwise regression approach to select a subset of predictors or features? Well, it turns out, again, we still have an overfitting problem. What lasso regression actually does, it introduces what we call a penalty parameter, where it shrinks the regression coefficients to 0 that don't adequately minimize the error. In a lot of your machine learning techniques are going to have one or more penalty parameters that are introduced. What gives it the machine learning flair is that the penalty parameter is selected through, again, withholding part of the sample. In this case, it was done through what we call tenfold validation. What that means is we split up randomly the data set into 10 pieces. We're going to fit the model in that first set, withhold that 10th. Then we're going to shift. We're going to withhold the next piece and fit the model and everything else, and we go down the line. And so we're going to average over the data to select a penalty parameter. So in doing so, we're slicing the training data set just like we sliced the original data set. And that gives us our machine learning flair to avoid as much overfitting. Now, it's not to say we can't overfit with machine learning. I'm going to actually show you an example later on from Google. It was a rather big fail. Not to pick on Google, there's been fails all around. That's just a rather famous one. So overfitting is not just restricted as a problem to traditional statistics, but machine learning minimizes the chances that's going to happen. So what are the key takeaways from this example I just showed you before I launch into the rest and definitions and whatnot? Well, one of them is that the machine learning methods split data into training and test data sets. There are many ways to do this. We used a simple 75%, 25% split. Sometimes you can go 50-50. Sometimes you even use validation or cross-fold methods where you split the data, fit it on everything else except one little piece, and then you go down the line. Why would you use one method versus another? I don't have a fast rule of thumb except to say that it's somewhat sample size dependent. If you have a big enough data set, you probably want to just split it, maybe even a 50-50 split. As your data set decreases in size, you have to get more creative. But when I say decrease in size, you're going to need a big data set. That's one key about using all these approaches. And actually, that's a reason why we're talking about the approaches today, because chances are the data that you're working with is going to be rather large. So machine learning methods right off the bat are probably well suited for what you're doing based on that. Certainly not the only thing you want to look at, but that's one of the key things in order to apply it. You need a lot of data points. I mean, in this example, we had 716. There's no hard and fast rule, more is better. You know, if you think along the lines of Google and some of these companies, they're in the millions of data points. You don't necessarily need that many, but I would say, you know, you want to think maybe around 1,000, you know, as a lower bound. We had 716, a little bit low. So if you're like me, some visualization kind of helps to drive this framework home. So there's these two key points to it. You know, first we have to use the data to learn. And so on the lower left-hand corner of the diagram, we have this training data. We feed it into the model. In this case, it was a lasso regression. We say the model learns, which just means there's some kind of automated procedure. You know, there's a penalty parameter we introduced. We shrink parameters that are not minimizing the error to zero, something like that, some kind of learning algorithm. And that gets fed into it and it develops a model. And then we move up into that red box where we have the task that we actually want to do. Once we have the model, we've moved past the training data. Then we feed in the features from our test data and we get an output. You know, the output might be, if it's a continuous variable, we might be actually predicting values. If it's binary, which is really the focus today, it's more on classification. Are we actually able to classify something? Last point I'll make on this example before moving on, we had really two goals here. It was partly descriptive. We wanted to understand associations between individual predictors and outcomes. So it had a descriptive goal, which was along the lines of traditional statistical methods, but we also want to build a predictive model. So lasso regression strikes a nice balance because it gives you, it's a regression. So it gives you an interpretable set of regression coefficients. In this case, I didn't show it on the slides, but we actually got logistic regression coefficients out of it. So you can look at that and we know how to interpret that. As we move into more complex models that possibly do a better job for prediction, things like what we call random forests, neural networks, and other methods, we don't actually get interpretable parameters out of the model, or less interpretable, I should say. So that's why these are sometimes referred to as black box approaches, not black blocks. Sorry, it's a typo on the slide there, I just realized. Black box approaches. So there's a trade-off. You know, you might get really good prediction, but if you don't understand the parameters that well, sometimes that can be a little scary. So that means you really have to carefully evaluate what's coming out of your model. Does it make sense? So again, I'll go to some fails towards the end. Okay, so now let's launch into definitions. So I just talked about lasso regression. That really falls in this machine learning area. We've got random forests, neural networks, and whatnot. So the way I set up this slide, and this is what's, I think it's fair to say it's pretty common. There's a lot of, you know, there's somewhat ambiguity in some of these definitions across the field, but I felt pretty safe in presenting it to you like this. AI, artificial intelligence, we can generally say is a big umbrella, and it refers to the science of training machines to perform human tasks. So AI doesn't refer to any one algorithm, any one method. It's really an umbrella term to describe the whole field, training machines to perform tasks. So machine learning is one group of methods that fall under that, and loosely we can say machine learning methods are methods to automate model building. And that was the lasso, random forest, neural networks. There's something else called deep learning, which are basically these neural networks, but they're on a larger scale. And I know I'm throwing these terms around like neural networks. Don't expect you to understand that. I'm just using the terms that are out there. You could easily spend, you know, a number of talks on that. So don't feel bad. You don't understand that, that's fine. Just throwing the terms out there. Under this umbrella, we can also put things like computer vision, image recognition, also natural language processing. So for today, the remainder of the talk, I'm going to talk a little bit more about machine learning, but also natural language processing methods. If we further subdivide machine learning, generally we talk about supervised learning, and that simply means that our outcome is well defined, as it was in the regression example. We know what it is. We just want to come up with a set of variables to better estimate it, classify, whatnot. The other area of machine learning is unsupervised learning. This is where we get into clustering algorithms, where we don't come in with pre-specified labels for the outputs. So for today, and it's fair to say, I think most of what you would be interested in would be the supervised learning, because you know what your outcomes are, you know what the results are. So let's just briefly talk about some specific use cases. One is if we think about write-in survey responses, certainly applicable for CHIS, certainly applicable for census surveys. You know, we can think about, in line with the theme today, if we have write-in responses for other categories on race, ethnicity, what do we do with that? You know, sometimes it might be obvious, but people sometimes as people are people, we misspell words, we're in a rush, we don't even write out the word completely, words might blend together, we don't write what we meant, all kinds of things. So if we think about the option in dealing with this, well, we could have somebody sit down and look at what people wrote and try to manually code that. Obviously, that would be pretty subjective, probably pretty inefficient, error prone. So we actually think of more automated coding schemes. And this is actually what the Census Bureau and other agencies have been doing for quite a while. Somebody does sit down and check work and does some audits on what the algorithms are doing, but largely they rely on automated coding schemes. So the first step of an automated coding scheme is you got to pre-process the text responses. What do I mean by that? Well, everything from removing the spaces, correcting misspellings, changing uppercase letters to lowercase, whatnot. You basically want to give your automated coding scheme uniform responses in terms of, so when they see the words, they're the same every time. So if I write, for example, African American, if somebody misspelled it, didn't write it out completely, we want to correct that. If one person puts one white space in between African American, somebody else puts two or three, we want that uniform for the machine to recognize. Once we've done the pre-processing part, there's really two ways we can do this. When you think about it, we can take the responses as is. We can have a pre-existing dictionary of responses and try to do a match. So, once we do the pre-processing, say with African American, we can look at a dictionary of responses and say, great, African Americans in the dictionary, we know how to classify. Well, that can work great sometimes, but as we know, there's a lot of variations in the way things are recorded. So we might want to actually rely on some machine learning methods, natural language processing methods. And so thinking of some limitations with the dictionary approach right off the bat, multiple entries may not, even if you have multiple entries in your dictionary, it may not catch all the variations. I mean, think about if somebody fills in a response and they write, well, I'm mostly African American, or they write, I'm half Black. I mean, you can think of all your own variations. There's quite a few. So actually coming up with a pre-existing dictionary that catches all these variations might be kind of difficult. Another limitation is the dictionary doesn't actually make use of responses to other questions that actually may help with the classification. For example, names and surnames, geographic location. There was actually an interesting paper that used these other categories. I forget what country it was in. I think it might have been in Canada, something more recently. It was a +1 article. I'm using some of these other pieces of information to actually help classify race, ethnicity. So let's talk about what can machine learning offer. And I'm going to actually, again, show you an example. This time it's going to be a very simple example, just so we can work through it together and better understand the process of what's going on under the hood. So again, we're going to start with training data, as we did in the prior example. So whether you're working with, straightforward binary outcomes, continuous outcomes, whether you're working with text and you want to classify it, as in this case, the general machine learning approach is going to be the same. You're going to have some training data. You want to train the algorithm, and then you're going to see how well it performs in the data you withhold, test data. So in this example, it's going to be overly simplistic. Just to show you, let's say we have 4 respondents in the data, and we want to classify write-in responses as either, say, Black, African American, or not. So 1, 0. Obviously, again, very simple example. We would have many racial ethnic categories, but just for the sake of instruction here. And let's say there's 2 binary features, A and B. Those binary features might be, did somebody write Black a certain way? Or did they write African American a certain way? Did they use this name versus they didn't use that name? Again, we're probably going to have many features, not necessarily all binary, but for the sake of this discussion, 2 binary features. So in this example, what we want to do is we want to assign weights to A and B. Think about a regression. You would run assigning regression coefficients. And we want to actually create a decision rule to classify the respondents when A and B occur. So let's say we feel confident that we have this training data. We know that in the first row, when A and B occur together, that the ground truth is that this person meant to indicate they are Black or African American. So we want to make use of that information in the training data. So we can ask ourselves, what kind of weighting scheme can we come up with in a decision rule so that somebody gets properly classified as Black or African American if A and B are both selected? Well, there's a number of weighting schemes that will actually work. Very simple example, but one of them, if we assign A to be 4 and B to be 4. And if you go across the rows there and you see in the last column, if A and B are both 1, then that means that coding or that weighting scheme will give us a total of 8. And you can go down the rows and see the second line is going to be 0, the last one is going to be 4 and 4. So if we want to make sure that somebody is classified as Black or African American based on those two responses, or sorry, based on those two features, A and B, one safe way to do it is say they're going to be classified that way if the score, the weighting score from A and B is greater than 5. So if you look at this very simple example, you'll see, okay, that's a safe way to classify it. If a score is greater than 5, we classify them as Black African American. That gives us a correct score. Now we call this a linear classifier because we actually are drawing a straight line through the points and we're separating the points out. We've got essentially in this case, we've got the first respondent who's one side of the line, and we've got the other 3 respondents who are on the other side of the line. So this in of itself doesn't tell us much. We just came up with this weighting scheme in the training example. What are we going to do with this? Well, we would then fit this to our holdout data, our test data, and see how well does it perform. What is the error in what we classified and what people actually were. And what we can then do is take that information, we can feed it back and now treat that as training data and reweight. We can come up with a new weighting scheme that makes use of that information and come up with a better classification. Now, we don't have time to go into all the details today. I'm kind of looking at the clock here to make sure I don't go over. But that's in real brief, that's the general idea of one possible way that we could classify and evaluate. Basically we want to evaluate how our predicted classifications matched the actual classification in the test data. And then we're going to tweak the weights based on the classification error. Now you might look at this and say, well, isn't this kind of similar to the dictionary approach? I mean, in that first iteration, you are using pre-existing features that you feel pretty comfortable with, and that's kind of like a dictionary. You see if the features match. If they do, you classify somebody as such. Well, yes, absolutely. In that first step, there is a similarity to the dictionary approach, but what the machine learning approach allows us to do is then update those weights and update how we decide somebody gets classified. So in essence, we iterate to update our quote dictionary. Now, with machine learning, again, with these black box approaches, we might not actually even understand what the dictionary is that creates the matches. And that can be bad sometimes. But on the plus side, a machine can often come up with a much better dictionary than a human can, based on what's in the data. It can see the patterns that we're unable to see based on that. So there's always this trade-off. The machine can come up with something, but it's really our responsibility to check it. Are people really being classified as Black, African American as they indicated? I'm just going to talk about a second use case very briefly in the interest of time. And the second use case is around inverse probability sampling weights. Now we know in survey research, we use inverse probability of sampling weights for a number of things. If there is attrition and we need to account for certain segments, say certain racial ethnic groups having a higher proportion of non-response, missing values, we want to account for that. Similarly, if there's imbalances in the data and health services research, we use propensity scores sometimes to try to balance across, say, if there's health insurance status and we know that people self-select to get health insurance. If we try to draw some conclusions on that, we need to account for that self-selection somehow, and sometimes we use propensity scores. So inverse probability sampling weights have a number of applications in what we do. Well, if we think about one standard approach, what's the first step to coming up with an inverse probability sampling weight? Well, we got to estimate a probability, whether it's a probability of having a missing value, a non-response, a probability for being self-selected into a particular group, whatnot. Got to estimate that probability. Well, the traditional statistical approach is to fit a logistic regression to estimate that. And, I mean, as I've done, and we all do when we tend to fit these logistic regressions, as a general rule of thumb, we probably put more into the model than we need. And, we take the safe bet. We were not always sure what should go into that model to estimate the probability, but sometimes you end up putting everything in but the kitchen sink, as the expression goes. Well, is there a better way to do that? It seems like, if we had a better set of predictors to estimate those probabilities, we would come up with better sampling weights. Well, what has been found out in recent years, that's actually indeed the case, and machine learning approaches can help here again. One such method is called generalized boosted modeling. You use that to estimate the probabilities. We don't have time to go into details, but I'll just say it basically draws on the principles we talked about, where you withhold some of the data for test data. You fit the logistic regression or this boosted whatever other method it is. Usually it's regression tree models, which that's a whole other set of models. You fit it to the training data and see how it performs. And then you refit, reiterate, and you boost. That's why it's called boosted modeling. You actually boost your predictions going in subsequent steps using these regression trees. I listed a textbook that has a little blurb on this, and there's certainly a lot of good research articles out there that talk about this. So for the last few minutes I have talking here, I'm going to just touch on things like software and some caveats. So what do you use to fit these types of models? Well, this slide here, I have a 7-year-old, so she definitely influenced my choice of graphics, but hopefully it helps to kind of visualize. The three things that I generally try to think about is striking a balance between what I need. If I need do I need a complex model? It's powerful. And when I say powerful, do I have a lot of variables, a lot of features that I have to throw in? Are there nonlinear relationships I expect? Are there interactions I have to worry about? As the complexity of the model and the data increases and what I'm trying to draw from it, I need to think about more powerful models. So power is something I have to think about. Flexibility. Is this software or programming language going to let me fit different types of models? That's something else a concern I have sometimes. And the last thing, user friendliness. It can be the most powerful software in the world, but if I can't use it, it's not going to do me a lot of good. So these are basically the three things I think about, and I listed in my opinion, these are three ways that people tend to go. You know, the one you probably hear about a lot among data scientists is Python. What is Python? Well, Python is a programming language. So Python itself doesn't do machine learning, but there's been a lot of libraries that have been written for Python that do perform machine learning. So Python is a popular choice for data scientists. Do you have to learn Python? Not necessarily. R, which is being used increasingly among both data scientists, health service researchers, everybody, R is a really nice middle ground. You know, it might not be as user-friendly as some of the standard software packages, but it's fairly user-friendly and it has a lot of power to it. There's a lot of stuff you can do. So R is actually, I will say that's my default choice to go to. I will start with R. If I really can't fit something in R, then I will go to Python, but I'll confess R is my default. On the bottom there, I have Stata. Now, Stata is great software. I use it for a lot of things in traditional statistics. It's just coming to the table as far as offering machine learning algorithms. And that's not to pick on Stata, that's the same for SAS. Pick your favorite standard statistical software, that's true across the board. They just don't have as many features. There's an emerging language called Julia. It's gaining ground among data scientists. It doesn't have a lot of users yet. It doesn't have a big community, but the word on the street is that it is actually faster than Python. So if you really have a big data set and speed is a concern, Julia is a direction you could go. So just a little bit more talking about these programming, software, other considerations. If you have a simple machine learning approach like the lasso regression we talked about, you actually have a lot of options. You can use any three I talked about. So for example, let's say I want to use Python. There's a library I have up on the screen there. That library can fit a whole host of machine learning algorithms. Let's say I want to use R. That's what I actually used in that first example I gave you with information health seeking. GlimNet package. It's a great option. Can fit binary outcomes, continuous. Stata 16. They've actually introduced some routines for lasso regression for both continuous outcomes, linear regression, as well as logistic. And there's even something in there for instrumental variables to boot. So Stata 16 and other packages are catching up. Besides the running the model itself, another consideration is data management. And just stop me, AJ. I'm trying to look at the clock here. I forgot exactly how much time I have, but I might be going over a little bit.
I think you're doing just fine. I think everybody's super interested, so please keep going.
Okay, cool. All right. I tried to kind of keep it within the time slot, but I might be going over just a little bit here. So another consideration, data management. You can certainly import your data into any of the three options I mentioned. Python has some good data management libraries. R, certainly if you use RStudio, it makes it pretty easy to view your data and do other things. And of course, if you use Stata or any of the standard software packages, they make it really user-friendly for you to see the data, view it, and whatnot. But sometimes you actually want to go outside what the capabilities of what they offer. You actually want to use separate data management options. Why would you want to do this? Well, there's a number of reasons. One is, and Databricks is certainly just one option. I think it's a pretty good choice. That's just a personal preference. There's certainly others. What is Databricks and why would you want to use it? Well, Databricks is cloud-based. So, sometimes that's one reason if you want to be able to have data accessible across universities. Of course, there's HIPAA and other things you should think about, but if you want to share data, using a cloud-based solution like Databricks makes it really easy. What's another reason you'd want to use something like that? Well, another reason is sometimes you got to pull in data from multiple resources in different formats. So for example, think about medical chart data. You know, you've got the actual labs, you've got physician notes, you've got possibly external data you want to pull in. Databricks actually makes it really easy to pull data in from various sources, different formats. And you can actually run Python code, R code within the Databricks framework. So everything is there. It's a little bit like, well, it's not quite like that. I wanted to say like Jupyter Notebook. Jupyter Notebook lets you run code from different programs, but Databricks is just more all-encompassing. So that's another thing, the data management side, a consideration. Lastly, I just want to mention computing options. You know, separate from what program you're going to use, how you're going to manage the data. If you have a really large data set, running something on your desktop computer, I know my poor health policy management students, when I teach the class in the spring and they have these data sets of 30,000 observations, and some of them it takes a week longer to run some of these. They're not even doing machine learning, just with standard regression approaches. It can take a long time to run. So you can imagine with machine learning, it is more computationally intensive because you have to split the data. Everything just takes longer. So one of the options you have is to draw upon cloud-based resources that you can access. So I just listed one here at UCLA. There's certainly many institutions that have them. At UCLA, we have something called the Hoffman 2 cluster. What the Hoffman 2 cluster is, it's a collection of computers. So if you want to run an algorithm, you can split up the tasks among the computers and have things run in parallel. So this gives you a lot greater power in doing so. Well, so why wouldn't we just always do that? Well, the trade-off is you have to rewrite your code so it can run through a parallel computing system. So there is that trade-off. But you know, again, if you get with a really large data set, is it worth it to rewrite my code so I don't have to wait a week, a month? Yeah, probably. So those are some of the trade-offs, but it is kind of a steep learning curve, I'll just tell you, with rewriting some of your code for parallel computing. I'm going to end with some caveats. These are just general things that you can pull from the internet, and they're out there. Some of them are kind of humorous, some of them are kind of sad, but regardless, they're warnings for all of us. There's a rather famous one, a big fail with Google, and not to pick on Google. Google's great. There's many companies that have had fails, but one of their famous ones is Google flu trends. And I think this was back around, I want to say 2008, where they got the bright idea, can we use what people search for, whether maybe it's cough syrup on Google or, different medications around flu season, can we match that up with the CDC flu tracking information and actually predict, flu trends around the country? Maybe we can help out the CDC even. So they had really good intentions. Well, it initially worked, but then it failed. Why did it fail? Well, there's a number of reasons that people have brought to light. One of them is that they took a model, they fit it to data that was relevant for that 2008 season, or whatever the year it was, and then they tried to use the same model moving forward. Well, that's a classic case of, it's a sense that's overfitting, because your model parameters you developed in 2008 fit that data really well, but they don't work so well in a new data set. There's other issues that are classic to what we do in health policy research, omitted variable bias. In machine learning, we talk about predictors. Well, there's danger in using that word because it may not literally mean that X predicts Y. It may mean that Z predicts both X and Y, as a classic example of omitted variable bias. So simply using machine learning doesn't remove that obligation to really think through some of those concepts. We can't just rely on the machine. We still have to have the human involved to know, does it make sense? And another problem, which is actually related to omitted variable bias, overfitting, simply time varying predictors. There were temporal changes in how people searched, did the Google searches across seasons when the flu season came around. So if you're using your searches from 2008 and trying to extrapolate for the next year or subsequent years, might not work so well, and it actually didn't. And a huge problem with this to point out, their model was so complex, it was also proprietary, so they didn't really want to share, but it also, I think even Google themselves didn't understand it completely. It was kind of hard to disentangle why it didn't work. So that's something to really keep in mind with these approaches. Even if it's a black box, you really have to evaluate the model carefully as best as you can. Another thing, issue that comes up, missing data. So moving to the machine learning world does not remove that problem. Certainly we can use machine learning methods to impute missing data, but what happens if the features we are using to impute have missing data themselves? What do we do then? Well, if we think about standard regression approaches, whether we use multiple imputation, single imputation methods like hot decking, methods are pretty well established. You come up with a multiply imputed data sets, and those data sets have the same covariates or features across the data set, so we can average the effects. Well, if you think about what machine learning typically does, it typically selects a subset of features. It typically looks at nonlinear relationships between the variables, interactions. That's really the strength of these machine learning methods. That creates problems if we're going to impute multiple data sets. What if we select different features across the data sets? How do we then average those features like we typically do with multiple imputation? Well, there's no clear consensus in the literature. I'll just say there are numerous approaches. One of them is you can stack all the imputed data sets together and fit one big model. You do need to use weights. You can also analyze the imputed data set separately and then come up with decision rules if what gets selected doesn't match. If you say if over half the data sets select this variable, then we're going to include it in the final model, but there's no hard and fast rule. I'm just going to give a shameless plug here for a paper that looks like it's going to get accepted in psychological methods. I worked on with a couple of my postdocs. They did a really good job, so I want to highlight them too. It's a discussion on these different methods. We give a tutorial on how to apply them and a little bit of a comparison. So hopefully next year this will be out in psychological methods. But for the time being, there's a whole host of articles that discuss just this issue. And lastly, I'm going to leave you with this note. At the end of the day, it's really important to remember that the AI, machine learning algorithms themselves, they're not intelligent. We say artificial intelligence, but the algorithm's not intelligent. It's really up to us to ensure data diversity. So you have to have representation across the racial ethnic groups, other indicators. So in my first example, looking at health-seeking behaviors, it was really important to include people of different racial ethnic groups, different sexual orientation, gender identities, the age groups were rather limited for that one, but other characteristics, people with health insurance, people without, people using substances, people not. So you really have to ensure data diversity. Otherwise, the algorithm is going to end up with very biased inference or going to lead you down a way you don't want to go. And at the end of the day, we have to understand what the algorithms are doing and not capable of doing. In the Google fail example, obviously in the long term, it worked in that one flu season, but it wasn't really capable of working down the road. So understanding the limitations, it's up to us to ensure that all these algorithms are implemented in a sensible, equitable, and ethical manner. I'm going to leave you on a couple of notes, the last two slides. One is, this is a rather humorous example, and this is pretty much infamous. You can just do Google searches and find just gobs of these. This company developed this InspiroBot to see if an AI algorithm could come up with inspirational posters, put a nice picture with some inspirational words. Well, actually, it didn't work so well in a lot of instances, what it came up with. I mean, you look at the first one on the left, before inspiration comes the slaughter. The one on the right there might be a little bit more accurate. I don't know, basing your everyday existence on science creates loneliness. Maybe that's a little more accurate, I don't know. But, at the end of the day, these are some pretty big fails, right? So again, the algorithm is not intelligent. It's only going to do what you tell it to do. It's going to just make use of the data you give it and try to do the best. On a more serious note, I just actually pulled this up, this article, The Death and Life of an Admissions Algorithm, from the University of Texas at Austin. They actually kind of, not secretly, but they kept it sort of hush-hush for a while. They were actually using a machine learning system to evaluate applicants for its PhD in computer science program. Well, what's the problem what they did? Well, they took past acceptances and rejections and looked at the features, the characteristics of people who got into the program and didn't, and fed that into a big model to use to weed out applicants in the, for future admissions. Well, obviously that's pretty problematic if you want to introduce more diversity in your applicant pool. If you're rejecting people based on who got in the past, that's not going to work too well. So they actually, there was kind of pretty large outcry, understandably. I don't believe they're using that algorithm anymore. But these type of examples constantly pop up that we really have to be careful how we apply these algorithms. And I will stop there and now turn it back over to you, AJ.
Thank you so much. And what a great way to end. Some of those posters were just, I admit, when you first put them up there, I was like, well, those are bizarre. And your example makes absolute sense. Okay, so I want to get to questions, and a reminder to everyone, if you have any questions for our panelists, please put them in the Q&A and we will get to them. Our first question is, how did you determine the weighting rule for A and B of 4, for 4A plus 4B? And there was a follow-on to that. In general, in your first use example, how do you determine the weights and the decision rule?
Yeah, those are good questions. So I'll address the first one about how did we determine the weights of 4. We looked at those rows, and the first row was the only one where someone self-reported being African American or Black. In the remaining 3 rows, they didn't report that. So that was our training data. So we could fairly make use of that information to come up with the weighting scheme. So we actually wanted to then come up with the weighting scheme where we use the feature information to weight properly. So what we noticed in the first row is that when somebody is 1 for both A and B, then they also report being African American or Black. So that's the key. They have to be 1 on both in order to come up with being African American or Black. So whatever weighting scheme we came up with, we wanted to set up a scoring system so that when they reported for both A and B, then they would be put in the African American Black category. So the reason why we came up with 4 it was somewhat arbitrary in a sense because you could have used a range of scores. That was just an example, but the key was that by using the scores of 4, if we looked in the far right column, we ended up with 8 for that first one, and then 4, 0 or 4 for the remaining. And so we knew that whatever scheme we came up with, the decision rule had to be so that you had to have a score greater than 4 in order to be classified as African American or Black. So the weights by themselves don't have meaning. It's the weight in combination with the decision rule where you look at the features and say, okay, this combination, we need to think of a weight, and that feature does that. What, I'm sorry, there's a question there too. Oh, I'll get to just a second here. So that's what you do. So now in that example, you know, that's just visually, you can look at that table with the 4 rows and you can visually come up with the weighting scheme yourself. As the algorithm gets more and more complex, there's actually automated equations that lets the, you know, the computer actually comes up with the algorithm. So hopefully that helps to some degree.
Great, thank you, thank you. So are there any resources like books or papers for understanding what type of data we need, not just the sample size, but type, and what questions we should use machine learning to answer?
Yeah, that's a good one. So I would say that there's 2 common types of resources. You know, one in this example with the writing responses, that's all going to be focused a lot on what we call natural language processing. And, you know, there's whole textbooks just on natural language processing. There's one, you know, I like the R books because they give a lot of practical examples of how to actually do these analyses, and they point you in the direction of the libraries and what to use. So for natural language processing, actually, you know what? Just let me step away for a second. I'll grab and put this in the chat. So I apologize, I didn't get all this into the slides. It probably would have gone even longer, but I can put this in the chat. This is one book that I kind of like. Can I just type this in the chat here? Put it in, I'll put this to all participants. It's called
Okay, that'd be great. I'll plan to listen to attendees.
It's called Text Mining in Practice with R. And the author is Ted Quartler. So I'll hold that one up. It's got a wizard on the front. That's one I like for natural language processing. And so that really, what I like about it is it gives a lot of examples. It breaks things down. The book that I like, so that's one variation. When you get into just strictly quantitative data, you know, that was the first example I gave where, say, you know, you want to not predict, but you want to classify a response where it's quantitative. That's that whole group of machine learning algorithms. The textbook that I like particularly for that, it's called the authors I can think about, and I'm kind of biased because James Gareth is the husband of Catherine Sugar, who is a great statistician in our Department of Psychiatry. And the authors are Gareth, James, Everett, and it's Tib Shirani. Let me just do this really quick here. I think it's called Introduction, yes. An Introduction to Statistical Learning. And you know what? I'll do this. Let me see if I can drop this into the chat too, as we're talking here. Let's see. What I like about that book is that also gives a lot of great examples, and it provides a nice bridge. If you're very familiar with traditional statistical methods, it's a good bridge moving into the machine learning world, because a lot of those examples build off of regression. It is written in R. You're going to find a lot of stuff in R. I'm sorry, I don't have good examples for Stata or SAS. I think partly because the machine learning implementations in both of those software packages are so new. I just personally haven't seen a lot of great material out there yet. The Stata manual has some nice examples for Lasso, but even then, I don't feel it's on the level of like a textbook that really goes into a lot of details and makes it necessarily easy to understand. Let me put this in here. There we go. So that's another textbook. And what's great about an introduction to statistical learning in R, I believe the PDF of the textbook, like a lot of textbook nowadays, are actually free to download. I believe that's still the case. So that's another one that I would recommend. So really, if you get into this, you're going to have to learn a little bit on the natural language processing side with text, text mining and whatnot. You're going to have to learn a bit on the, the strictly the quantitative side, working with numerical values.
Okay, that's great advice. Our next question is, with ROC curves in the machine learning context, how are we using it? Is it checking how well the predicted values in the validation data set, oops, my thing just went up, are matching up against the test data set?
You're actually, that's a great question. You are actually testing the ROC, or not testing, you're calculating the values that go into the ROC curve in the test data. So you want to see how well your model actually performs. If you take, the parameter estimates you got, you plug in values from your test data, and you want to see how well it actually performs using the real values, the observed outcome values in the test data. So you have your classifications, what you predicted, and then you have your actual values, and you want to see how well those match up in the test data set. And that's actually the truth with whether you're doing ROC curves or any of these fit statistics, like even R squared. You really want to know how well that performs in the test data. And that's really been kind of the dirty secret of traditional statistics all along, is we have all these great fit statistics, but we just evaluate them in the same data we're using to fit the model, and we're not really getting an accurate picture of how well the model is going to perform.
Thank you. Christina, who is still on, says that her team is working on classifying race and ethnicity of roughly 500 students in our program. A primary challenge is classifying the quote unquote other open-ended text responses. Are there any options for us to use machine learning on our small data set, or would we be better served to just analyze them manually?
For that sample size, and I deal with this a lot, I would say it's probably not going to be the answer you're going to like. You're probably going to want to do it manually, honestly. Yeah. We deal with that a lot with the other category, and in all these machine learning algorithms, especially with text responses, it's all about that signal to noise ratio. There's a lot of noise when people enter text responses, and you need really large data sets. So I would say with what you're dealing with, with the other responses, you're probably going to have to manually code.
All right, so it's not the answer to everything.
It's no, it's not. I mean, you can try if you can grab some stuff. One of the things you can do that even if you do some manual coding yourself, and in truth, these methods, it's never one or the other all completely. The example I gave with the using machine learning on the fill-in responses, whether you code yourself or use machine learning, the first step is going to be pre-processing. And so that's where, for example, maybe removing spaces or removing what we call words that don't really factor into anything. If people say and, write that in their response, it's not really helpful. So you can actually, that book that I mentioned, the text mining and practice with R, there is a lot of great, I think like the first part of the book is all on R pre-processing libraries that can help you with everything from misspelling to standardizing, making everything lowercase. And then if you do that, you might actually find there's not that much variation in the other responses. You might be able to just then do a frequency table, once you get everything kind of uniform. So, account for all the different variations, it might actually be much more manageable, and you'll realize you don't even need the machine learning part.
Excellent. Next question, how do we determine or ensure adequate representation of key social groups to feed into the machine learning model?
That's a great question. So one of them I would say is we should always check how the model is performing. That's really the number one way. Because what's going to happen if the cell sizes are too small for certain groups, the model is not going to be able to predict membership in those groups. In a sense, those groups are going to be overridden. So if you have, let's say for an extreme example, let's say that you have, I don't know, 1,000 cases, participants or respondents, and you only have, say 5 people that wrote in responses for Latinx, African American, or whatnot, Native American, many other possible categories, the algorithm is not going to be able to pick up how it should classify if there's too few. And what's probably going to happen is it's going to classify them as white, or or Asian, whatever the large group is. It's going to classify them into that bin. So the easiest way to check if the algorithm is working, look at those groups with the really small cell sizes and see how did the algorithm actually classify them, on the output side of it. And that'll tell you really quickly if the algorithm's working or not.
Great. So I'm going to jump to another question here that I think follows on to that. In training the test data, is there a rule of thumb for when the results are considered optimal?
That's a great question. I wish I had a kind of a one answer. It really varies from field to field. I mean, in that first example I gave with trying to classify who uses the internet to search for health information, we were pretty happy with an area under the curve of it was like around 0.75, because that can save us money when we're designing digital health information to really target the people who need them and who are going to use them. We don't have to try to blanket as many people. So for us, not having a super high threshold, but a threshold that's better than a coin flip, still might be beneficial. But if you're working with something, say doing area under the curves, and it's something like, an automated cancer screening test, obviously 0.75, that's going to be pretty horrible. So, you know, in that case, you'd say, well, we can't rely on a machine to do this. So, and I would say the same for a lot of the important work that's done here with survey responses. You really want a high degree of accuracy to tell you exactly how high is acceptable. You know, there's probably layers to it where if it's really close, nothing is going to be perfect, but if you say get above 0.9 with accuracy or something like that, you might feel pretty good. If it's lower, it might still be worth it for you to run the algorithm, but have a human spot check some of the cases you think are going to be more difficult. It's just, it's hard to come up with a, you know, just a hard and fast number on that. But, you know, of course, higher is always better. It just really depends on the specific application.
Thank you. Similar to the previous question on other race, could machine learning approaches help with multiracial categories or those that check all that apply? This respondent is working with data where students can identify up to 10 different Asian ethnic groups.
Yeah, it definitely can. And again, you know, it depends on the sample size. The larger the sample, the more varied the response the algorithm is going to be able to handle. So I know that I gave very simple examples that were binary in classification. What a lot of the machine learning algorithms actually do when you have data that's, say, multinomial, you know, multiple classifications, what they'll actually often do is put the pieces together where maybe it's, say, African American versus everything else, Latinx versus everything else, Asian versus everything else. And you'll have those individual predictions, but it puts them together to see, can we come up with a multiracial classification or something like that. So you can certainly do it. You know, you can use, that would be a good example where you could use a combination of what the boxes that people check off on the response categories as well as what they write in. So, you know, you might combine first looking at, okay, if somebody checks off multiple response categories for different Asian ethnic groups, you might use that, but then also look at, oh, what did they write in? Does that add additional information to what they checked off in the boxes? And maybe the machine learning is sensitive enough in the data that's fed into it where it can actually pull out that information. I've just generally, what I've worked with, and you know, there's obviously a lot of scenarios. I found that it's sometimes tricky with the groups unless you have large sample sizes. You know, I'm used to some of those categories, like unfortunately Native American and some of them like Asian Pacific Islander and some of the groups. They don't have a lot of representation in the data sets. And so it's hard to get an algorithm that's going to, you know, give you a high degree of accuracy on the training. So that's the biggest concern. Can you do it? Are there algorithms out there to do it? Absolutely. It's just a case of if your data set is going to really be large enough.
Great, thank you. So we're gonna have a question that's not as technical as the others, and I may also invite our director, Dr. Ponce, to weigh in on this because it's policy related. How much importance can or should we accord to machine learning findings in advising policy interventions in developing country settings?
Do you want me to start, Scott?
Yeah, go ahead.
Well, I think it's not just developing country settings. I think it's a general question on importance of using ML for policy interventions. And I think it all kind of boils down to what Scott talked about towards the end in terms of, again, a diversity of the data, and then that it's the humans that make these assumptions in machine learning. So we want to ensure that that there's representation in the data and there's representation in the assumptions and inputs that get to the machine learning to ensure that what the policy advice or intervention is the target that gets at that. So I think that there's again, it's just, I believe, kind of a way of what I learned today, Scott, was the overfitting problem, where you can get to, it can fit for that one particular flu season back in 2008. So it could fit for the average consumer or the white the non-Hispanic, non-Latino white population, but it may not fit for certain subgroups. So I think a lot of it is just being very conscious about the bias that goes into the algorithmic biases. But it's also, it's not the monopoly of machine learning. Any kind of statistical predictive analytics also kind of bear this responsibility in being used to decide, where testing sites should be in COVID-19, where vaccine allocations should be. So again, I do think that there's a role for it, but there has to be diversity in both the data sets and the people that are making these assumptions.
Yeah, absolutely. And, it's a great question because it reminds me, I just went in on a kind of one of these network grant proposals to NIH, and they want to use Google Maps to look at, to gauge the friendliness around schools. And they want to do this in South Africa and Kenya and some other African countries. The reason I bring it up, there's a couple of lessons learned from this example, is that on the surface, it sounds like, this might be useful. Machine learning can certainly be used in the US and other countries to figure out how best to direct resources. For example, if we can find out, well, this school environment is not safe, or I don't know, not psychologically friendly. I forgot the exact word they were using. But we have to be really careful to know that, is the money going to be well spent? So in this particular example, when they showed the proposal to me, the first thing I said to them was, well, I don't even want my name on this because you're never going to be able to show what you're proposing to show. It was something like 9 schools across 3 different countries. And so I said, there's no way that this is a waste of money. There's too much variation. You need a huge sample size if you're going to use Google Maps to use. So, and I think in that case, they listened, and it's probably going to work out okay. But I see this a lot where people get kind of goo-goo-eyed over hearing words like AI, machine learning. They think, great, let's apply it. There's all kinds of grant proposals going out, and especially, unfortunately, I feel like Africa and other places, we kind of view them like testing grounds. Like, well, whatever we do is going to be better than what they currently have, and let's just try it out and see if it works. And it's just, we really have to be careful in what we apply. It certainly can do a lot of good, as we've talked about, and can certainly be beneficial for health policy, but we really have to consider all the details. It doesn't make sense. Is it likely to work in this situation?
Thank you, Scott. We're at the end of the hour. AJ?
Yes, so I do want to be sensitive. We did have 2 more questions if people are willing to hang around, but I also know that this is, time is very valuable these days. So I just wanted to give last few reminders before we sign off. We do have a few upcoming scheduled workshops. Please check back to our website to when we have new dates for the new ones in the new year. And everybody who has joined us today, please, oh, I'm back at the beginning, sorry. Please, in the email that you got today, the reminder, there is a link to a survey. Please share your thoughts with us about other topics and technical assistance areas that you would like covered. We greatly appreciate it. Dr. Kamalata, thank you so much for this presentation today. You took a topic that I think is new to a lot of people, but is very exciting and very timely and emerging. And you did an excellent job of making it very relevant. And we appreciate your time and thought. And I'm sure if we had audio for everybody, you would hear lots of clapping right now because it was an excellent presentation. And I want to thank you very much.
Oh, thank you. It was a pleasure being here. Thank you, AJ and Inez, and everybody else. Really important work you're all doing. So this was great.
Thank you, Scott. Powerful, flexible, accessible, really great. Thank you. Could you follow up with a question that we did not answer? And maybe we can just type it on the chat. It's on the other R-based texts. Would you recommend?
Oh, yeah.
That's also my question too. So thank you, El Brima.
No, you know what, that's a great question. There are definitely, you know what, I have seen in the Dummy series, which those are great books. There is one I've seen in the bookstore on like data science for dummies or things like that. I don't know that they're specifically R based, but there are definitely in those series. I'm just trying to think. It's kind of hard because I feel like there's so many textbooks out there that I'll have to think if I think of some good resources, but there definitely are. The Dummy series has some like machine learning, data science, and things like that.
Thank
Great.
you. And then the very last question, if you're willing, are there specific examples where having a data set that's representative of a diverse population leads to more accurate and useful results?
Yeah, there's definitely good examples out there. I'm just trying to think of, well, for example, we probably don't realize this, but actually machine learning has been used by the Census Bureau for quite a few years now. A lot of it has been behind the scenes and people don't always realize it. We don't realize a lot of times machine learning's been around since the 1950s, I think, or so. We just didn't have the computing speed back then, and there were some major breakthroughs that had to happen. One of them being we didn't realize we needed diversity in the data. There was, I think, a UC Berkeley professor who paved the way for that and said, well, you have to have diversity. And at first people said, no, that's ridiculous. If you want to train the algorithm, you just keep giving it more of the type of cases you want to find. And she said, no, you actually need to give it diversity so it can better hone in. And so today that seems obvious. Back then it wasn't. So these algorithms have been around for a long time, and the Census Bureau, they actually use them partly for the write-in response example I gave with the auto coding. That's already being used. And so I would say there's a lot of really fine work that's being done. It's not always perfect, but I think there's a lot of really dedicated, certainly smart data scientists that are working in areas for the Census Bureau and labor statistics and other areas where machine learning is currently being used.
Fantastic. Well, thank you so much. That is the end of the questions that we've had for today. We hope everybody had a great experience. Have a wonderful holiday season. Be safe and healthy, and we will see you all in 2021.
Yes.
Thank you.
Thank you.
Thanks again, Scott.
You're
Thank
welcome.
you.